So now our next speaker is Devavrat Shah. He will speak about medium access use.
Thanks, Sergey. So first of all, thank you all organizers for the umbrella program and the workshop. And hopefully I will have a chance to show my gratitude to them concretely in the talk. So be intrigued. All right, with that in mind, I'm going to talk about designing a distributed, efficient, medium access algorithm for wireless networks. And we would like to utilize queues or backlog information to design these algorithms. And as you will see, it's a method for those who know this for stochastic processing networks or a class of them. This method naturally extends. It's a joint work with my student Jin Wushin at MIT. What I'm going to do in the talk is first I'll quickly go through context. I'll define the problem. Then I will tell you a brief history of the question. Then I'll give you the algorithm. And hopefully in the rest of the time, I'll try to give you the proof intuition that why it works and some open question. Okay. So here's a sort of 1.5 slide of context. Imagine any reasonable engineered system. Then some form of resource sharing is essential, because if you're not sharing resources, then you must have badly engineered the system. Now, if you are sharing resources, then some form of contention must arise, and if there is some form of contention is arising, you need resolution of contention. There are a variety of examples. One would be, say, classical Ethernet, where there are a bunch of computers that are trying to send data over one wire, let's say, and at a given point of time, only one of the computers can send data. Question is that who sends it? That's a contention resolution question. Closer to this talk would be, let's say, there are a bunch of wireless transmitters that are trying to share medium, and some transmissions will cause interference to some other of them. And the question is that how to figure out a collection of wireless transmitters transmitting simultaneously so that they are not causing interference to each other. And this question is already sort of been asked and studied in this program already a couple of times. Okay, and what we want is an algorithm that is efficient, that is utilizing resources efficiently on one hand. On the other hand, it's extremely simple, and the sort of simplicity comes for a variety of reasons, and one of the primary reasons is you want minimal cooperation to reduce, in a sense, protocol overhead, one way to think of it. And the type of information that's available is very minimal. It's like, I'm a node, I'm asking whether a resource is available or not at a given point of time, or if I try to access it, I will, at the end of my attempt, I will come to know whether I was successful or not. It's really stringent. Now, philosophy is the following, right? You want to know pain about something. Let's say there are a variety of pains in life. One way to understand really pain is to feel it, right? So sort of how stringent is this, are these constraints? One way to do is to sort of feel it. So I'll have to make you feel it. Okay. So here's a clever game, at least I heard from David McDonald in one of his talks, and I've got a reward. And the reward is, so I obtained the information from somebody here that this chocolate, which is on 21st St. Andrews Street, just beyond Sydney Street, it's pretty good chocolates. I tried some of the truffles; they're good. So this is a giveaway.
Is this supposed to be pain?
Sorry? No. First, you have to go through pain, and after that, it's a reward. Okay. So now I award you reward, at least promised, and it's here. The question is that sort of what's a game? Okay. So game is following. When you are asked, you're going to raise your hand, and that's how you're going to respond very quickly. Okay. So 200 milliseconds. And it's not ill designed, like the human response time is 140 to 160 milliseconds, so this is reasonable. Okay. Now, if nobody raises hands or more than one person raises hand, nobody gets it. And if there is unique responder, he or she will get it. Okay. And I'll try to play it a couple of times just to make you feel. Hopefully nobody wins. And in that case, organizers will get it, starting from Sergey. Or let's say I'll share this with organizers. Good. I thought you will do that. All right. But okay. Who wants it?
Yes.
All right. Quite a few. Once more. I hope nobody wins. Who wants it? Okay. So this is for organizers, and if you want to try it, stick around.
I like like this game or not?
Sure. All right. So the point is the following, right? That in this kind of situation, I mean, if you are just starting playing, there's no hope of sort of you winning these things, and hence organizers winning, of course. But if, let's say, same sets of people are going to win, we're going to play it for hours and hours and hours, then maybe after a while, given that we are all intelligent humans, what we'll do is we'll figure out through this pattern of contention, some information is transmitting, and maybe there's some chance of we winning. There's coordinating. And the question is that through these kind of collision patterns, what type of information can be learned so that eventually some form of coordination can be achieved. And first question would be, can we even sort of constant fraction of time, can you win this from me? Or more generally, can you win it half the fraction of time? Or more generally, can you win it almost fraction one of the time? And at least I would try to argue that, at least in context of the question that we are looking at, it will be possible to win.
Does this count as a question?
Sorry?
Does this count as a
Question?
question?
You were raising a question.
Oh, no.
We're raising our hands.
No.
What have you done, right?
No. Well, game is over. Organizers win. But they will be happy to share. Okay. All right. So with that in mind, let me sort of define the problem precisely. And as we'll see, this, in a sense, this is exactly the type of question that we are trying to answer in a wireless network. So I'm going to think of wireless networks as formed of wireless transmitters, which are represented as circles or nodes here. Each node has its own some form of exogenous arrival process, which is bringing, let's say, packets. They're queued at there. When a node transmits, as shown here, its head of the line data departs at unit rate. And I'm going to assume for simplicity it's single hop, that is, once its transmission is done, the data leaves the network. Okay. Now, there's interference constraint. What it means, roughly speaking, is that if there are two wireless transmitters which are close to each other and transmitting simultaneously, then they're going to cause interference to each other, and we don't want that to happen. However, if there are far away nodes that are transmitting, then it will be fine. And the question is that how to design collection of wireless transmissions so that simultaneously transmitting nodes are not interfering. And one way to think of them as, here is a sort of a interference graph that is a simple abstraction of this model, where nodes are, again, wireless nodes. Edges between them represent that these two nodes cannot transmit simultaneously. I'm going to assume this simplistic model. Of course, one can imagine more complications coming with technology, but at the bottom of it, it's this simple model that matters. Okay, so with this in mind, what we want is we want a simple medium access algorithm that decides what non-interfering nodes transmit at each point of time using local information. I'll quantify it as I go along, with the goal to maximize the utilization of wireless medium. Now, I'm saying utilization of wireless medium, so I ought to define what resource is here more precisely. So that's what I'm going to do next. So it's the same graph, just remove the queues. So we have these nodes. Let's assume that each node has some arrival process with data arriving as per packetized arrival process of rate lambda is a Poisson process. I'm going to assume packets are unit sized. So in unit time, lambda amount of work is coming. Each node can transmit at rate at most 1. So clearly, we don't want lambda to be more than 1. But there are interference constraints, and those are the ones that are going to impose constraints on what is feasible, right? And so I would like to quantify that next. Now, a set of non-interfering nodes are essentially independent sets of this graph, right? That is a subset of vertices that are none of them are neighbors of each other. Okay, so let's say as some part of some algorithm at time 0, say these two nodes are transmitting because they are not neighbors of each other. Maybe at some other time things change and some other nodes are transmitting, or at some other time these two nodes are transmitting. So effectively, if you look at over time, as part of any algorithm, at each point of time, one of the independent sets is providing transmissions. So the effective resource is defined as nothing but the convex combinations of these independent sets. And more formally, if I'm thinking of, let's say, use the notation, say the set I is a set of all such independent sets represented as a vector of 0, 1, then effective service rate provided by any algorithm must be of the following form. It's a convex combination of these independent sets. And the interpretation of, say, alpha sigma in this convex combination is just fraction of times the specific sigma schedule is used by some algorithm. Okay. So that means the resource is nothing but the convex hull of all these independent sets. And given that we want an algorithm that is maximizing utilization of medium, one way to say is that as long as the demand imposed on the network is can be satisfiable, that is, it's in the convex hull of this independent set, then we would like to have Qs to remain finite. Okay. So that's a basic goal here. All right. Here's a bit of notation just to sort of keep us grounded. The Qs are, so vector of Qs is represented by bold Q. Qs evolve as follows. So it's the natural evolution that Q at time t is what you had at time s in past, plus what arrivals happened, minus what departures happened as per the scheduling algorithm. And I'll use this notation of sigma of t, which is vector of zeros and ones subject to independent set constraint, that is decided by medium access algorithm. Okay. Any questions about the setup notations? All right. So I want an algorithm that decides this sigma t every time, so that as long as whenever system is underloaded, Qs remain finite, roughly speaking. So now I'll describe a brief prior work. There's a lot of work on this topic, and it's a very active topic even now. So it will be impossible for me to do any reasonable going through history. What I will do is, for the purpose of this talk, I'll just divide work in two types of works in this context. One is sort of practically motivated random access like solutions, and then the second one will be performance optimal algorithm, which is Q-based algorithms, and then I'll go to our result.
One general question about the equation is you have no feedback?
No,
The arrivals are exogenous, right? So it's not as if things get recycled into system.
no. So for the purpose of this talk, I'm just going to assume single hop, but I mean, as many of these things in a natural way extend to multi-hop kind of things. It's just sort of part of well-known machinery. Thank you. Okay, so yeah. Okay, so here is a here's roughly how these random access algorithms look. So each Q is going to check medium regularly, and whenever it checks medium, so the way it's going to check medium regularly could be randomized, could be deterministic. When it's going to check medium, it will try to find out if any of its neighbor is transmitting or not. So there is this information that's available if any contending node is transmitting at a given time or not, that a node can access. It's called carrier sense information. Okay. And when it learns about this medium information, if medium is free, it attempts to transmit with some probability. And if it's successful in transmission, then it will retain the medium for a while. That's called W. Okay. And this is the type of algorithm that's repeated by every node. Okay. And the P's can be changed, W's can be changed, and that's sort of what brings in variety of variants of the classical approaches. So let me describe one classical approach, which is called exponential backoff, which many of you might have heard of. So roughly speaking, it goes like this, that every time you want to transmit a fresh packet, you will first attempt to transmit with, say, probability 1. If you fail, then you will sort of say, well, there is a congestion, let me half my probability of transmission. With probability half, you will attempt in next subsequent time slots. So on average, in next 2 time slots, you will once more transmit. Suppose you failed again because of contention, then you will further half your probability. So now it will be 1/4, and so on till you are successful. And once you are successful, you will get a new packet and you start again. Okay, and those are the types of protocols that are or variants of them that are well studied. Okay. Now, as I mentioned, there's a huge history. Now, these algorithms that are one way to look at them is they're really naive form of message passing. There are no explicit messages are passed, but there's just information that's gathered through these contentions. Okay, and but on one hand they're extremely simple, on the other hand they're hard to analyze, and maybe they're poor in performance. So there are a variety of positive and negative results that have been established, and many of people sitting here have actually worked on this problem extensively. So I'm going to there is a nice website that's maintained by Leslie and Goldberg in UK that has history up to 2000. Some of the results that are sort of ongoing post 2000, I'll sort of leave at the end a slide of them. One result that I would like to take a note of is by Hastad et al. What this says is that in the context when there's one resource that you're sharing, not exponential backoff, but polynomial backoff. So remember the algorithm I described, you're backing off exponentially. There is half, 1/4, 1/8. Instead of that, you with kth failure, you back off as a function of k, which is polynomial, with exponent alpha greater, exponent of polynomial strictly greater than 1, then it will be positive recurrent, as in the system is efficient. All right, so that was as far as random access algorithms were concerned. Now coming to this max weight algorithm, so it's not about simple, it's just about performance. And as many of you have seen this, it's like a natural generalization of longest queue first algorithm. That is, you have one server, you want to serve one of the n queues. Which one you serve the longest queue. In this context, you have choices. Choices are options. So for example, in this case, one option is you serve 1 and 2 at a given point of time, and you will choose that option if its weight is the maximum among all possible options. Now, what is the weight of this option 1 and 2? It's sum of their queue sizes, which is 30 plus 30, which is 60. Okay. Another option is serving 3 and 4, but their weights are 45 plus 10, and then which is 55, which is less than 60. And the way I have chosen the example, 1 and 2 is the maximum weight. So you choose that to serve, and hence your schedule will be 1, 1, and rest are 0. So those are the transmissions happening. Over time, let's say arrivals happen, departures happen, queue sizes change. So you will change your schedule, and let's say now you're transmitting as per this. Okay. So this is the max weight schedule. Yes.
You have different information. In previous case, you looked at the medium, and here you looked at this length of the queue. And what kind of information you shall use in different? Everything depends on this information.
Thank you.
What's the connection between these two cases?
Correct. So connection. Okay, there's no connection first of all. As I said, the first class of algorithms are simple random access based algorithms, which are primarily motivated by designing extremely simple protocols. So you're utilizing very little information. This one is just a good performance optimal algorithm. Okay. It was introduced by Tasilas and Ephremidis, and it has all sorts of interesting properties. However, it is not a simple algorithm. It is complicated. It is centralized the way I described, and in general, it's for the purpose of this model, it's trying to solve this max weight independent set every time, which is a hard problem, as we know. So it's unlikely that this algorithm has any use. So what I'm trying to present is following status quo. So on one hand, it's a sort of a picture. So the random access algorithms are great in terms of implementation, possibly not as good as what we want in terms of performance. These max weight like algorithms are great in terms of performance, at least reasonably good, but as is, they're far from what we want. So what we want is something which is best of both worlds. And here is a sort of an ideal solution, right? At least I like to say that. I would like to have an adaptive random access based algorithm that uses queue sizes, but in effect ends up simulating or performing like max weight. If that happens, that will be very nice, and in some sense, that's what we are trying to do, and that will be our algorithm. All right, so now I'm going to tell you my algorithm. Okay, so since I promised you that it is at random access like, going to sort of fit into the template I presented earlier. So as before, each node is going to check medium regularly. I'll define this precisely in a second. The things that I have to define is what the probabilities are and what time duration it is going to keep. So the probabilities are always going to be 1, and the time duration will be some function of queue size. So once you acquire the medium, if you have longer queue, you're going to keep it for a while, as in longer. If you have a sort of shorter queue, you're going to keep it for a shorter while. And that's essentially the crux of the algorithm. And the right choice of function will be important. You can't just choose any function. There is a sort of certain property we would want. A reasonable thing that you would like to think of while I'm describing the algorithm and until I come to intuition is think of f as a log of queue size, so logarithm of queue size. Okay. All right. So now with that in mind, let me describe the algorithm. I'm going to describe two versions of algorithm. First, I'm going to describe something called continuous version, and then I'll come to discrete version. The continuous version, nodes have carrier sense information. There is information that is any of its contending or interfering neighbor transmitting. It will have that information instantly available. So in one hand, it's an idealized assumption, but it will be easy for me to explain. And then I will describe version where that information is not immediately available. That is, it's a delayed, and that is discrete time version. Okay. So with that in mind, let me start with continuous time version. So here, each node has an independent exponential clock of rate half. Say. It says that once in 2 time steps, 2 time amount, the node's clock is going to tick. When a node's clock ticks, it's going to do the following. It's going to first look at its own decision. What was it doing just before? If it were transmitting, that is the first part, then it will decide to continue with high probability, or it will leave the medium with probability 1 over function of queue size. So this is sort of will make sure that essentially on average you're keeping medium for f of q amount of time. Okay. Now suppose you were not transmitting when your clock ticked. Okay.
So if you interrupt, then it means what happens with the message you were transmitting before?
So I'm going to just sort of what do you say? I'm for the purpose of this part, I'm sort of assuming that sort of have this continuous amount of message.
Okay. It has been transmitted everything.
Yeah, yeah. And I'll come to discrete part to sort of, but I just want to sort of start with this description. Good. Okay, okay. But suppose you were not transmitting before, then you're going to check medium if it's free, and in this case you will have instantaneous feedback available. And if medium is free, you will just take it. Okay, and because of this continuous thing, there's no sort of collision happening at the time you are choosing. So here's a caricature of, just to explain and make sure that I really explain the algorithm well. Let's think of this 3-node setup, and suppose at some time node 1 is transmitting and node 2 and node 3 are not transmitting, and those are their queue sizes. Now let's say this node's clock ticks, it decides to sort of, it was transmitting at this time. So with high probability it should continue, with small probability it should give up, and that's what it's doing here. So let's say it decides to leave the medium. So now nobody is transmitting. Some time passes. After some time, let's say node 3's clock ticks. Okay. Now it sort of senses the medium, instantly it learns that nobody is transmitting, so medium is free. So it's going to, with probability 1, it's going to acquire medium and start transmitting. So after some time, this node's clock ticks, sees that there is one contending transmitter is transmitting, so it can't do anything, and it will just do nothing. Any questions about the algorithm? Yes, please.
Where do you take 1/2 for the rate?
Constants are not important. 1/2 is chosen because I wanted to make sure that visually it looks good, and I'll explain in a second. but half is not important. It could be 1, it could be 2. Okay. So here is a discrete version, and I wanted to match half. That was the reason. So discrete version is that each node in the beginning of time slot makes a decision, and the way decision is made is as follows. First, with probability half, it's going to toss a coin and say, is it going to do anything or not? If it says yes, I'm going to do something, then it does the following. So just like before, if you were transmitting in previous time slot, then you will continue transmitting with high probability, but with probability 1 over function of your queue size, you will decide to leave the medium, as in not transmit in this time slot. Okay. Otherwise, what you will do is you will sort of see if the medium was free in the previous time step. There is nobody who was contending with you was transmitting. If not, then you will transmit. Now, of course, in this, what's going to happen is that many of us will try to possibly try transmitting. That will result in collision, and so you're back to sort of square one. That is, it's not success. And the next time you repeat as if you're in this state. Okay.
Next time what?
Next time you repeat as if you were not transmitting. You will sort of. Okay.
What is clock rate?
Sorry.
What is clock rate?
Probability half. It's just Bernoulli process with parameter half. There is a node sort of has a probability half of coin, which half it comes up 1, half it comes up 0.
For each time step?
Each time step. Okay, any questions? Okay, so I mean, then I have sort of successfully conveyed what I wanted to convey mainly. It's exactly halfway. Okay, so here's the result. Both versions are efficient, as in it's the underlying Markov process is recurrent when it's underloaded. Now there is to establish this result, we need a modification of weight as follows. So the way I explained the algorithm, you're using f of q size. I need regularization, which is as follows. It's maximum of the function of q size times square root of the max of q size across the network. Now, instead of max of q size, you could use some reasonable estimate of it, and that would still work fine. And one could design some such estimate based on sort of a bit of information exchange. But we strongly believe that this regularization is not needed. Now, there is a way to get rid of this regularization without exchanging any information, where through these collision patterns, again, you can learn an estimate of Q max. So effectively, there could be an implementation that takes care of, that designs the algorithm where you're not exchanging any information, however, operating all based on just collision information. Okay, but we believe that this is not needed. So that's one open problem. Okay, for example, for graphs like simple graphs like complete graph, you can show that it's not needed. Okay, now next I'll tell you the proof intuition why I need certain conditions on F. Yes, two questions. Yeah.
Yeah, so the hardest recurrence you get whenever, not always, right? Because not always.
Of course,
whenever you have arrival rate in the interior.
In the interior, of course. Thank you.
What does it mean that algorithm is throughput optimal in this theorem? This theorem, what is it? What does it mean?
Sorry?
What is it sense of what does it mean that the algorithm?
That's what I meant by when I, yes, it is, that means the following, that when this arrival rates are in the interior of your capacity region, then the Markov process, appropriate Markov process, is positively recurrent. In this standard sense.
You have, for any algorithm, you have some parameters when your Markov process is
That's correct. So
very accurate.
yes.
What to tell after that?
That's just called optimal in this jargon. That's all. It doesn't
Yeah, I
have
mean,
optimal.
all it says is that there is no algorithm that will sort of be positively recurrent outside the capacity region as we know, right?
They use the word optimal, but nothing is being optimized. It just means that the stability region is achieved. That's all.
So
It's just jargon.
But for any algorithm, you can find some stability region.
Correct.
For example, if you have no input.
Okay. All right. Okay.
It's a max sketchable region.
Thank you. So there is a parameter space. Here parameters would be, let's say, arrival rates.
Yes, you have some arrival.
Correct. So sort of for example, you could have an algorithm which is not very interesting. You could have this small region, and what I'm trying to say is that this is a region which is sort of essentially largest possible. In that sense, it's optimal.
So the theorem is that for this algorithm, this region is maximal.
Correct.
That's the correct terminology.
In which sense? In which sense it's maximal? For any other algorithm, you cannot find what you have many parameters. So in the space of parameters, you have different sets of for.
All right. I'll try sort of 25 seconds. If not, we'll talk afterwards. So let's imagine it's a 2Q system, and here is sort of, say, capacity region looks something like lambda 1 plus lambda 2 less than 1. Okay, so then this is the capacity region. A bad algorithm will be something like this, where it's positive recurrent here.
But it is simple case. But if, for example, you decide that you put all your resources for lambda 1 only,
Yes.
then you have not this simple picture. You have for
Correct. So sort of depending on what your demands are, if there exists,
This is my question. In which sense your set is maximal?
Stabilizes whenever it's stabilized.
Right. That's the
But
right
it is not true, because if you shall take one queue only and put all your resources on your first queue, then for lambda 1 you have different.
Okay, how about this? In interest of my time, I shall continue, but I would love to sort of talk to you.
But
Can you explain the role of WI in the algorithm? We have to go back to the previous slide. What's
Good.
WI going to do in the notation?
Good. I have sort of introduced notation without defining it. Replace f of f by this thing.
Oh, I see.
Thank you.
The notion of Harris recurrence that you have there, what kind of assumptions does it make on the arrival?
Good. Good. So, for example, if you have any reasonable arrival process, let's say bounded second moment IID, for example, that would be fine. Poisson, of course, would be fine, and so on. Okay, fine. I mean, go optimize. Okay. All right. Okay. Now I want to tell you why sort of the choice of f is like this. So first, let's forget small o. It's essentially saying roughly scales like x, but in exponent it's small. Okay. So at least this is how we arrived to the algorithm. See, in this, the way algorithm is designed, you have schedules which are sort of evolving over space of independent sets of the graph, and then there is a queue size which is changing. And the way you evolve these schedules, those rates depend on the queues. Okay, so there is sort of two types of dynamics. There's the queues that are changing, and then there are schedules that are changing. So let's first assume that there is some form of time scale separation, i.e., queues are not changing. Okay, so queues are fixed. In that case, what's going to happen is the schedules are forming some finite state Markov chain on the space of this independent sets. And more importantly, it's a very nice Markov chain, at least in the continuous case. It's what's known as, at least in physics community, is Glauber dynamics. It's a reversible Markov chain, and it has a very clean stationary distribution. And the distribution says that as per the stationary distribution, the probability of choosing certain independent set or schedule is proportional to exponential of this quantity, where this quantity essentially says that if I'm going to look at one particular schedule and I'm going to define its weight as sum of the logs of its q sizes that are part of this schedule, then the probability will be proportional to that. So what this says is that suppose I have q's fixed, and let's say my algorithm is running infinitely fast. Then at any point of time I see that what schedule is chosen by the algorithm, it will have this distribution, and in a sense it's choosing a schedule with higher probability if it has higher weight.
This is basically the Jiang-Wall-Round algorithm.
No, this is not.
It's actually the same intuition behind it. Yeah.
I'll come to that. I have a slide for that, but thank you. Okay. So what this will say is that first of all, it's sort of choosing schedules with higher probability if it's a higher weight. More importantly, it is close to the maximum weight in the following sense. That is, in expectation, its weight is close to the maximum weight, and the constant sort of depends on the system side but doesn't scale with the q size. So if I have q's fixed and if my algorithm is running extremely fast, then what this says is that I'm essentially scheduling as per max weight scheduling, and that's the reason sort of this type of algorithm might work. However, if you chose any f, then it may or it may not work, because the question is that we want to figure out when is this time scale separation reasonable to assume. Okay, and that's where the choice of f becomes crucial. So let's sort of try to sort of look at what will happen when q's change. So let's see that suppose pi t is the stationary distribution corresponding to the Glauber dynamics on independent sets, assuming q of t is given. Okay, so of course qt changes, this stationary distribution changes, and let's say mu t is the distribution on schedules that is induced by the algorithm, which is changing with q's, of course. Okay. Now let's say initially we started with some bizarre state, and that's actually where we want it to be. Now it is possible that, well, I'm going to run the algorithm for one step, so since we know that Markov chains are sort of nice, so it's going to move towards, in one step it's going to move towards this pi 0, but now q's changed, so the pi 0 moves away, so pi 0 will become pi 1, and then maybe next step you move from mu 1 to mu 2, which is closer to pi 1, but then pi 2 goes away. So now the whole question is that, are you going to get close to pi t or not? If you get close to pi t, then essentially you are sort of operating in this nice state all the time, otherwise you're going to operate in this sort of a bad state, and that's when time scale separation doesn't hold. Okay. And this is where the choice of f becomes crucial, and one way to sort of figure out whether it converges or not is to try to look at one step evolution. I think that how does pi t change in unit time step, and here by change I mean in chi-square distance, and how does mu t get close to its pi t in unit time scale. Now if the ratio of these two changes are following this inequality, that is mu t is getting closer to its distribution faster than the rate at which pi t is changing, of course sort of this kind of thing should hold. And here is a very rough back of envelope calculation, but gives the intuition. So as a part of this algorithm, the way I described, the change in pi t is roughly related to, say, derivative of the weight function that we used, f of q, or f prime of q here, right? And mu t is related to 1 over fq to power n. This is essentially 1 over mixing time, and mixing time we saw in the last talk. And I'm putting just worst case estimate. For n node graph, this is the worst possible. Okay. So as long as this is faster than that, we'll sort of reach the convergence. And this is what this means. So we want f's that satisfy this property. So here I'm sort of simplifying everything, and I'm just trying to sort of show you this just one variable. So of course it's different, but tries to give the intuition. Okay. So this is the condition we want. Now if we were trying to use standard max weight, that is f of x equals to x, then what will happen? Well, f prime is 1, and this is 1 over q to power n. Of course, for large q's, this is not going to be satisfied. So that's why standard max weight is not going to work, and if you were curious, you could actually take a simple topology, grid topology, and try to run this f of x equals to x, and you will see this nice usual instability curve, that is, q's will sort of build up at a rapid rate. So, okay, while that's not a proof of or a counterexample, but I don't believe it will work. Okay. And that's okay. But if you have f of x equal to log x, then of course f prime is 1 over q, and this is polylog q, and clearly for large q, this will be much smaller than that. And that's the reason this type of choices of f's will work. Okay. So essentially what we are doing is a part of this algorithm is we are choosing f's which are somewhat aggressive, but not too aggressive as a function of q size. Because if we had too aggressive functions, then they are doing unstable things, and they will induce instability in the system. If they're too little, if they're slow enough, then somehow the observation of the system that is matters for the control of the network, that is function of q size, slows down, and that's why sort of network becomes controllable by this distributed algorithm. Now, here sort of is in some sense a threshold, right? There is all the functions that are growing faster than this will not work, all the functions that are growing slower than this will work. So I've got this whole gamut of functions, which function to choose. Okay, so I don't have a theorem, but I have some simulations. So let me explain what the simulations say. So we look at a 20 cross 20 network. It's a sort of a 400 node network. It's a grid network, and you plot total queue size in the network over time. Okay, so it's just a time evolution of the system. Now, there are two plots that I want you to observe. One is the green and one is the purple. The purple is the one which uses f of x equals to log x, and the green one is the one that is using square root of x. So this one is more aggressive. That one is less aggressive. So what's happening is that the more aggressive one has average Q small, but there are wild oscillations. And the less aggressive one has average Q's large, but they're sort of a lot more stable around that average. So it's naturally suggesting that, well, slower f's, what they're going to do is they're going to lead to smaller variance, but larger average Q size. Sort of makes sense. That is, you sort of first suffer cost in terms of average, and then sort of you're really stabilized. Yes, Tim?
Is the square root function, is that even stable?
No, as in sort of at least not as per theorem, but for this this particular topology, square root works, but x won't work. X you will see, so it just climbs up.
Square root x, where stabilized system?
In simulations.
Oh, okay, so in theory we don't know.
Yeah, in theory I don't know. But you could sort of use some other functions like x to power 1 over n, which you can prove that it is stable. Okay, so all right, so that's the algorithm and the proof intuition. Now in remaining 10 minutes, I'd like to take you through a few other things. Now, so what this says is, okay, we wanted throughput, we got it. Here's a sort of a simple class of algorithms that give you throughput, and assuming that after the talk I'll convince Raipko that it is throughput optimal, then we have a good throughput algorithm. But what about queue sizes? Now, queue sizes are in a sense a transient property of system. For algorithm, I suppose this class of algorithms, the transient property of this random walk-based algorithm is their mixing time. And naturally, in this case, they do relate in up to polynomials very cleanly. But in worst case, the mixing time could be very large in this class of graphs. Okay, and it could be exponentially large in number of nodes. Now, if I go back to the max weight scheduling that I described you early on, not only it's throughput optimal, but for even simple max weight, the queue sizes scale polynomial, in particular n square in this particular model with number of nodes. So the basic question that is here is that, well, what we wanted was throughput, then we wanted good implementation, and now we are looking for queue sizes. So how do these three performance metric interplay with each other? Okay, now of course finding that answer exactly would be very hard, but here is some attempt. And so here's a question that we ask. Let's say that I want an algorithm that achieves at least 50% of throughput, is a constant fraction of capacity. Okay. And I want good queue size scaling, and then I want good implementation cost. And question is it possible? So what I just described you on last slide, if first I put that requirement, and then I ask, can I have polynomial queue size, but let's say I'm happy to suffer in terms of complexity, then of course max weight would be a good candidate. Okay. Let's say I want simple complexity, say for example algorithm I described, but I'm happy to suffer in terms of queue sizes, then that's the one algorithm. But if I want both, then it's a hard problem, and it's not possible unless computational hypotheses are false. So what this says is that clearly if we are expecting to have all three together in general, then it's unlikely to happen.
What about polynomial queue size?
Good. So actually this one is better.
Oh, the erasers are down here.
Oh. Thank you. All right. So so there are two parameters in some sense. One is the rho, the loading of a system, say rho of lambda, and second is number of queues. Okay. For the model I described, max weight average queue sizes can be bounded as n square over 1 minus rho of lambda, and I don't want to worry about this scaling. That's why I said let's fix rho up to half. So this is always between half and 1, let's say. Okay. So given that this is constant, now I'm looking of scaling dependent on number of queues in the system. And when I'm talking about polynomial, I'm thinking of polynomial dependence on number of queues. Okay.
So you're claiming in your algorithm you have exponential queue sizes in the number of queues?
Number of queues, yes. I mean, it's large.
What's the rationale behind that? I mean, why would you sort of the network at such a scale? Because let's say that you have local degree in the network or something, right?
Yeah, so unless there are assumptions that you put down.
Yeah, if you have finite degree in the network, you're not going to see it as such an enormous scale.
No, not necessarily. I mean, because mixing time could be horribly large. Okay.
Also these ideas of Neely and so on to try to correct for the queue size by centering the queue size around which you do this kind of algorithm.
Well, I mean, but I'm just stating that it's just not possible.
It's not possible.
I mean, that's one way to go, but look for solutions. The other way says, well, unless we believe that P is equal to NP. So, yeah.
Maybe actually. And hope that P is equal to NP.
Okay.
Destroy most of computers.
Restart. All right. So that's one way to look at it as a pessimistic result. Other way to look at it as well. I mean, actually, maybe just sort of we are not sort of stating the question right, because I mean, do we expect sort of in practice networks to be sort of horribly complicated? Well, no. I mean, networks should have some reasonable structure. Maybe one reasonable structure is saying that, well, not really random network, but maybe polynomial growth style networks. That is, if network is in some geometry, and if nodes have some minimum distance, and if nodes that are contending are on local distances, then the interference graph that you have cannot be too complicated. And in those situations, with some local cooperation, we can do something interesting. But it's not as clean as at least the simple random access protocols. The question is that, can we get very, very clean answers for that setup and still have small queues? Or more generally, I mean, the way we assumed in this setup is that there's interference is a noise, or we want to avoid interference. But I mean, as an information theorist, one would say, well, maybe you could sort of do some form of interference cancellation. So how would try to incorporate interference cancellation in these kind of algorithms? Don't know. David, you have a question?
Yes, about using the special structure.
Yes.
This, the difficulty here seems to stem from the fact that the independent sets mix slowly
Yes.
on graphs.
Yes.
They do mix slowly even on grid graphs.
Correct.
So why would you hope that things go away if you look at the...
Correct. So sort of in some sense, one needs to sort of go beyond at least this class of algorithms. So here sort of we are trying to get some local cooperation to get away from that kind of algorithm. The question is that sort of how much cooperation can you eliminate and how much is needed? It's a bit vague, but okay. And then last slide, I promised Venkat, there is a slide I have on, so this is there's a very nice work by Jiang and Walrand, which is an alternative approach. It's done at the same time, and it is different because of the following reason. The way I understand, the philosophy is the following. Let's say you give me a lambda, the rate vector or the loading, that's inside the capacity region. I want to find access probabilities, the way I described early on, that are just dependent on the lambdas. So that if I use those access probabilities at each node by themselves, then with respect to stationary distribution, the effective service rate that I will get is larger than the lambda. Then in some sense what's happening is that each node, if I look at it by itself, the arrival rate is smaller than the service rate. So in that sense, sort of every queue by itself is sort of doing fine, and the whole network is doing fine. So the question is, first question is that are there such P of lambda existing? And second is how to find them. More importantly, how to find them in distributed manner. Okay.
And the
Yes.
nodes behave independently?
Sorry?
And the nodes act independently with these probabilities?
Yes. So imagine that sort of you, in the first version, the continuous version of the algorithm I described, where node just sort of, what is it, uses P's as sort of to determine the access. Okay. Okay. So first they showed that actually, okay, one way to think of lambda, or sort of existence of a good scheme, is to say that I'm going to find a distribution over space of schedules or independent set, so that as a effectively the service rate induced has that property. And they showed that of course there exists one such nice distribution which is a product form, and somewhat not surprising because it's a nice, it's a world of exponential family of distributions, and it's only boundaries that matter where you have to worry. But you know, when you are inside the interior, existence is not a problem. What they did, which is clever, is that so they said, well, let's look at sort of the max end way to learn this distribution. A distribution that satisfies those conditions that maximizes the entropy. Okay. Now, once you have that, then if you've sort of seen this type of things before, or worked this type of thing before, then the resulting distribution will be product form in terms of constraints. Okay. And for every constraint, you will have a parameter in your product form or in your exponent. Here, the constraints are per node, because that S is greater than lambda is per node constraint. So there will be parameter associated with it. So it will be of the form something like and these RIs have connections to the appropriate dual variable of that optimization problem. And so the question is that can you learn those dual variables in a distributed manner? Okay. And if you look at this optimization problem, they show that there's a very simple subgradient algorithm that needs to utilize this effective service rate given at a given point of time and the lambdas. And as long as you know those things, you can sort of learn those lambdas. The problem is that sort of can you learn it in a distributed manner without knowing anything about the network? And this is where, in some sense, there's a multiple time scales coming up. If at a bottom time scale, if things were nicer, let's say some compact space on which you're living, a parameter space is small, then sort of life would be great and you could sort of use standard stochastic approximation things. But that doesn't happen here. And that's why you need some form of incremental learning. And indeed, eventually, this approach sort of leads to rate stability. And of course, it doesn't lead to a positive recurrence. And our approach, which is Q-size based approach, which does provide positive recurrence. And if sort of we remove that learning part, then it is completely distributed positive recurrent. Okay. So with that, I'll leave this as a sort of, this is epsilon fraction of things that are happening. And I'll end my talk here. Thank you.
I have a question. Can you explain why you need the maximum of the Qs to prove stability?
Yes. So sort of there are two aspects, right? One is the change. Okay. So if you remember the proof intuition, there are two parts. One is how the change in distribution happens, and how the change in how quickly do you go towards stationary distribution. The second part is related to the mixing time. The first part is related to the change in distribution. And in order to have the change in distribution small enough for large Q, you need this property. Okay. Yes.
When you want to change the situation for transmitting your packets, you only consider this that's not Q size. Maybe it's not better to consider the Q size at the neighbor nodes, or for example, notify some other nodes with some bigger Q size.
Sure. So I mean, you would like that to happen, and sort of in some sense, through these kind of interaction, that's essentially what's happening. Yes.
Suppose there's one queue that's overloaded.
Yes.
You want to say maximize throughput.
Yes.
In some sense, is there any way to adapt your distributed version?
So this is general, as you know, this is general mechanics which sort of tries to bring in, say, some kind of rate control. So one way to say is that remove the overloading problem is to say that I'm going to do rate control at each node, so that effective rate allocation is doing something nice. For example, say maximizing proportional fairness, as in maximizing as per proportional fairness, and then subject to that you're doing the right scheduling. And in some sense, the way I described the algorithm, it's a max weight. There is a standard thing that people have developed which sort of uses max weight as a sort of subroutine. So in that sense, whatever algorithm I just told you will fit in well as a subroutine into that bigger mechanics, and then it will be a distributed way to deal with overloaded queues.
So my understanding is somehow in the Jiang wall round, you need to have some way of bouncing off the boundaries, right? And I think your Qmax is also doing something like that. So you're sort of recognizing that there's a large Q size at a global level, and you seem to be increasing your aggressiveness when you do that.
No, so
Isn't that what you do with the max of the new F?
No, I mean I think it's a technical condition, because
you really believe it's not doing the same. It's not dealing with the same conceptual issue.
No. I mean,
but that's the only global part of the Jiang-Waldron algorithm somehow.
Yeah, but sort of, I mean, for example, the one that sort of I described with incremental learning, you don't even need that. Basically, it gets you rate stability. It doesn't get you positive recurrence.
Oh, you already have an algorithm that doesn't require any global information at all?
Yeah, so that's what I meant by this one. So this is something that should appear in IT transaction this year. But it gets you rate stability, not positive recurrence. So it's sort of a last level question, who cares? Yeah.
if instead of independent set, consider matching. That's another reasonable toy model for. But matching global dynamics mixes fast.
So then
at the cost of best of worlds.
Yes. Yes.
My question. So assume that it's again. I continue with the method. So assume there is it's a mixing up. So assume that you know only local information about your Q size, no any centralized information. This here you don't know anything. You're learning everything.
Yes.
If you are allowed to know your Q size,
yes.
Is there a chance to get a positive current?
You're allowed to learn.
No. You know only your Q size.
Yes.
But you don't have any centralized information about centers. Is there a chance to get a positive?
Yeah, I think so.
Yeah,
I mean,
you have not.
well, okay, so I mean,
learning is dangerous, right? You might end up learning the network in the
Yeah.
Yeah, but so let's say sort of here sort of I want to know really sort of this some regularization basically, what I will call it. Question is that can I learn the regularization?
Yeah.
Let's say I believe very strongly believe I can do it, and if it's one sort of next month it's written up, I'll say yes.
Yeah. So it's hypothetically yes.
Yeah, hypothetically it's yes. So sort of.
No, but the philosophical issue is whether you're learning the network or not. Because once you throw learning in, you're really sort of cheating at some level. Because what are you learning?
Okay. Thank you.
Well, up to organizers.
Can you go back to the discrete time? Yes, so if, for example, we apply this algorithm to the chocolate game, it means that I have a clock which ticks with probability.
So every time sort of I ask you to raise your hand, with probability half, you decide whether you're going to think about changing your state from previous time.
Yeah, but I mean, in that case, if everyone raises his hand with probability half, there is only.
No. But probability half is to decide whether you want to change your state from previous time, and the state would be the following: whether you are raising hand in previous time or not. So suppose, let's assume that there's a world where sort of nobody was raising hand in previous time. Then sort of with probability half, now this time they will decide whether they should raise their hand or not. After that, what they do is sort of follows this rule. Okay, we can talk offline because I guess everybody is hungry. All right, thank you.
Okay.